Hey guys, this is Angel, and in this video we're going to be talking about Newton's third law of motion, which is briefly stated as, for every action there is an equal and opposite reaction. What I really want to do in this video is discuss some of the peculiar concepts that are really tough to understand, or at least they were for me, when it comes to this law. And so in this first scenario, we've got a box on a planar surface, and what we have here to the left is the force that the box exerts on the surface, and then what we've got right here is the force that the surface exerts on the box. Now this is different from the force of gravity on the box, because the force of gravity on the box is equal to the force of the box on gravity. So now that's really kind of a hard concept for me even now to grasp, and that's that the force the Earth exerts on us is the equal and opposite of the force that we exert on the Earth. So just I'm going to explain a little bit more about that later in this video, but in this case we've got this box that is pushing down on the surface, and the surface is pushing back on the box. Those are the equal and opposite forces. So what I've written here in orange is, although we say that the objects are in contact, according to our understanding of atoms, the equal forces are due to electromagnetic repulsion of the atoms. So what I've drawn in here are just little representations of atoms. And the thing that we want to understand is that nothing ever really physically touches. So even as you're holding your pencil or you're got your headphones in your ear and it feels like you're touching, it's never actually touching. And that's because an atom is formed of a nucleus that has a electron cloud around it. So I'm going to do my best to draw this cloud around my nucleus. And so in between that cloud is just open space. So you can't really ever have things touching when there are open spaces in that cloud, right? So even though I'm representing here, the little balls are representing atoms, and it looks like they're touching, they really are never touching, and what they're actually doing is repulsing one another. Because the electrons in that cloud are negative, that when they come to close to another electron, cloud, they repel one another, and that's what is causing equal forces to occur, so in opposite directions. So if you want to imagine it like so, this electron cloud is going to be repulsed by the opposite cloud and vice versa. And so that's what are causing the equal and opposite forces that are explained by Newton's third law. And so hopefully that makes a little more sense now as to how there is an action, equal and opposite reaction. That is different from field forces like gravitational force. That is its own, gravitational force is its own field force as compared to electromagnetic force. That's also its own field force. So when we say that objects are pushing on one another, what they're really doing is repelling at the atomic level, but we say that they're touching because it's just easier to understand that way. Gravitational force is a different field, and the Earth exerts a force on us that is equal to the force that we exert on the Earth. And that's all part of the balance of the universe, and we're going to discuss that a little later in the course. But now let's move on to an example of objects in motion. These are the laws of motion, so I thought it would be proper to include an example with motion. And in this scenario, we've got three phases. We've got the first phase where there's a gray ball moving towards a black ball at 10 meters per second. And then when the balls collide, when they touch, quote, they experience equal and opposite forces. So that means that this ball is now providing a force to the black ball in the right direction, and the right ball is providing a force to the gray ball in the left or negative direction. And again, remember, these never actually really touch. The reason that those forces are in the opposite directions is because their atoms are repulsing one another. So Now let's look at what happens after that. We've got here that the gray ball is still moving to the right, but now it's lost some velocity, and the black ball has gained a great deal of that velocity. So this, we're not going to talk about the momentum that's going on here, but what we are going to understand from this, what we're going to try to understand from this is that because this experienced a negative force, it experienced a negative acceleration, because whenever we have a net force, we have an acceleration. So this experienced a negative net force, and it was moving to the right, but it was accelerated to the left, or to the negative direction. And it went from 10 meters per second down to 3 meters per second. And for the black ball was at rest, but then experienced a positive net force to the right, and it went from 0 to a positive number, in this case 7 meters per second, in this partially inelastic collision. So they experienced equal and opposite forces, but because one was moving to the right and experienced an acceleration to the left, it slowed down. Not enough to cause it to completely come to a stop or go in the opposite direction, but it did have an effect on its motion. And then the object at rest, given a force, a net force, in the positive right direction, experienced a gain in velocity. And so that's just an example of how this equal and opposite reaction law, this third law, affects objects in motion. But now, I think probably one of the hardest things to understand is when big objects hit little objects, because it just doesn't really make sense that if you pull with 500 newtons on an elephant's tusk, that tusk is going to pull with 500 newtons back, even though the elephant is significantly larger than you. So, question: how does this make sense with large objects acting upon small objects? The answer: the objects will experience the same force, but because they have different masses, they will experience different accelerations. So let's take a look at the scenario here. Let's say that the ball had a mass of 2 kilograms, here, this soccer ball, and the person had a mass of 120 kilograms, so a very large difference, and kicked the ball with a force of 10 newtons while moving with a speed of 10 meters per second. What acceleration does the ball experience? What acceleration does the kicker experience? So I guess a question that I could have asked beforehand is, what force does the kicker experience? And that force that the kicker experiences from the ball is going to be equal to the force that the kicker gave to the ball, which was 10 newtons. So now let's go ahead and solve for the acceleration experienced by the ball. We can use our second law to determine the acceleration. We've got the force was 10 newtons because the kicker kicked it with 10 newtons. The mass was 2 kilograms, and so our acceleration is going to come out to 5 meters per second squared. So the ball experienced for a very short amount of time that the foot kicked the ball, it experienced an acceleration of 5 meters per second and was able to gain a velocity, and because of its small mass, that's pretty significant, 5 meters per second. Now let's take a look at the kicker. We're going to use the same formula, but in the same force, because the ball exerted a 10 Newton force on the kicker the same way that the kicker exerted a 10 Newton force on the ball. The mass, however, is significantly different. We've got a 120 kilogram mass, and so our acceleration, we're going to have to solve for that, and that is 10 newtons divided by 120 kilograms to equal approximately 0.08 meters per second squared. So that is a very small acceleration compared to the 5 meters per second squared that the ball experienced. And when we think back to real life scenario of this, we notice how the ball experiences a very large acceleration and goes flying off into the air, while the kicker maybe does experience this acceleration in the opposite direction, so we could even call that negative, experiences that in an opposite direction, and I'm sure that does have an effect on halting his foot just a little bit. And so hopefully that made a little more sense to you guys. If you have any questions or any comments, please leave them in the comments section below. Please give us a like and subscribe if you feel that this has helped you out and you want to continue staying updated with our videos. Thank you.